So hello everyone, thank you for being here. So in this talk we will be talking about a protocol that is inside the network. So we will be diving deep inside the IoT network. And more specifically, we will be talking about a protocol for authenticated key exchange, which is the protocol that needs to be executed before any encrypted communication can take place. So this is a protocol between two entities that need to exchange a symmetric key that will later be used for encryption. So I will, before going into the protocol, I will give you a little bit of a context around IoT. I've seen that previous presentations were already talking about IoT, so I won't focus as much on it. But I assume all of you are familiar with the concept and the IoT, Internet of Things paradigm, and the applications that it enables. So the applications, some typical applications are smart cities, smart homes, smart buildings, and some more traditional ones like industrial monitoring for different factory use cases. And what is important to understand is that the objects at the heart of the IoT are very constrained. And we are talking about objects that are powered by an energy source, a non-rechargeable energy source. So typically like something like AA batteries. And they are supposed to last on these batteries for several years. At the heart of these objects is a little microcontroller, a little computer that has small processing power compared to our smartphones or our laptops. So typically we are talking about tens of megahertz of processing power. We are talking about tens of kilobytes of RAM memory and hundreds of kilobytes of flash memory at the heart of these devices. So the devices do not have, they have no user interfaces. So you cannot just type in a password, for example. So we have to come up with solutions that are smart and automated in order to be able to configure these devices and to, for instance, let them join the network. And finally, the networks that interconnect these devices are constrained in nature as well. So this, I cannot stress this enough, because the network, apart from the device constraints, we have network constraints as well. And some examples of IoT radio technologies are like 6-dish technology standardized in the IETF, a multi-hop wireless mesh technology, LoRaWAN, which we heard about, or cellular narrowband IoT. So these technologies have in common device constraints, but also they have very limited capabilities for transmission of packets over the network. So we are typically talking about packets that are a length of an SMS, so 10 to hundreds of bytes for a packet, and the data rates are very limited as well. So in essence, we cannot be, in these networks, we cannot exchange a lot of data. We cannot transfer megabytes of data because it will take a long, long time to transfer over the network. And we need to be very efficient on how, on the protocols that we use that are going to be transported over the network. So as I said in the introduction of my presentation, we will be talking about a protocol for authenticated key exchange, which is a protocol that establishes a symmetric shared key between two entities. And a legitimate question to ask, obviously, is why can't we use the existing internet security technologies? For example, the transport layer security protocol, which is the de facto solution in the internet today, right? So I will be answering this question throughout my presentation today, but I would like just to give you a hint that the transport layer security protocol is very chatty in sense of how many messages it requires to be transported, and the corresponding identity technology, the X509 certificates that are used in non-constrained space take a lot of data to be transported over the network. And now, why is this a problem for IoT? I will give here, there are several aspects to this question, but I will give just some answer with respect to the 6-ish networking technology, which is a multi-hop mesh networking technology, and the network formation use case. So the use case when the device first joins the network, when you go ahead and deploy a network of like hundreds of thousands of devices, and you turn them on one at a time to join the network. So this is the network formation use case. So the thing is that at this stage, we have very limited bandwidth. We have even less bandwidth than is usually available in the network. And this bandwidth is shared by all the devices that are currently attempting to join the network. And the time for the network to form, depending on the number of packets or the number of round trips in the protocol that is used to do the authenticated key exchange for network access authentication, can be from minutes to hours, depending on essentially on the number of packets in the protocol. So what we will be talking about today is essentially the protocols that are executed after the device first hears network advertisements and recognizes the network, and essentially how it tries to join this network to become a legitimate part of the network and start sending IoT data. So I gave you a hint that these technologies, existing technologies, are possibly quite heavy for IoT, and within the organization called Internet Engineering Task Force, which is the organization behind today's internet, we are working on a lightweight security stack for IoT devices. So as a reminder, Internet Engineering Task Force is the organization that standardized, for example, the TCP IP suite in the form of open standards called RFCs, Request for Comments documents. And more specifically, today we will be talking, and in the Internet Engineering Task Force, there are hundreds of working groups that are split into 7 different areas, one of them being the security area where our work is taking place. So in November 2019, we formed a working group called LAKE, which stands for Lightweight Authenticated Key Exchange in the IETF. So a new working group was started in order to standardize an AKE, so an authenticated key exchange protocol for Internet of Things use cases. So I have the pleasure of co-chairing this working group, and we have just last week published our first RFC, which is the ad hoc solution document, the ad hoc protocol, which I will be introducing throughout my presentation today. So we have to differentiate between 2 concepts. LAKE is a working group, and then there is a solution protocol of the working group called ad hoc. So before we could even start about defining a protocol in the IETF, we had to go through, we had to define what lightweight actually means, what it means in practice. And here I give you a couple of metrics that we defined at the very early stages of the standardization process. So these metrics are number of round trips to complete, number of bytes on the wire, wall clock time to complete, and the amount of new code that the implementation of the protocol takes up on the device. And remember why that is important, because we have very limited memory. We have very limited memory on the devices, so we want to minimize how much space the protocol takes when implemented on the device. So the LAKE was formed in 2019 in November. And first thing we had to do is that we had to go through a process called requirements collection, essentially a first step in any engineering process, to collect the requirements for this protocol. These requirements considered both security requirements as well as performance requirements of the protocol. So this phase took place between November 2019 and June 2020. And in June 2020, we had an adoption call for a document, for a solution document to those requirements that we standardized, that we defined in the first place. So in June 2020, we adopted a protocol called ad hoc as a solution of the working group, and we kept working on it ever until last week. So this protocol was implemented in parallel as it was being standardized by different implementations around the world for all the participants who were interested in the standardization, different companies, but also different researchers and academics, academic participants. So in parallel with the standardization of the protocol, we had implementation effort going on and interop testing of the protocol, meaning that we were meeting in order to test the different implementations for interoperability, whether they can talk to each other and exchange a joint key successfully. In November 2021, we declared this protocol as ready for formal analysis. What that means is that we considered the work in the IETF being done, and we invited the academic community to study the protocol for any vulnerabilities in order to improve the protocol before it is published as an RFC. So this is the same process that was followed by, for example, the standardization of the transport layer security 1.3 protocol. And we had several teams worldwide answer this call. So during this stage, 6 months, during these 6 months, the protocol in the IETF was frozen. So essentially, there were no updates being done to the protocol. And the academic community was in parallel studying and publishing papers on the topic of this protocol. After the formal analysis kind of wrapped up, we integrated all the mitigations against the attacks that were found by the academic community, and we have specified new versions of this protocol in order to have it bulletproof for when it's published as RFC, which came last week. So the ad hoc was published just last week. Ad hoc became RFC 9528, and there is a corresponding document on ad hoc test vectors, which is RFC 9529. And right now, the working group is working on extensions to this protocol that I will talk about in a minute. Right now, I will go ahead and dive deep into the protocol and explain you how the protocol actually works. What is it that we standardize, and how is it that it differs from transport layer security, for example. So first, the security goals of the protocol, as they were standardized in the IETF, include some typical requirements for authenticated key exchange protocol. These are mutual authentication, confidentiality, downgrade protection from different downgrade attacks, security level, identity protection, and there was also a requirement of the protocol being standardized in Lake to transport third-party application on top, and we call this data external authorization data. So these were the requirements as they were collected in the IETF at the very beginning of the phase, and then the solution protocol ad hoc is the protocol that meets these requirements. So ad hoc is an authenticated key exchange, again, protocol, which establishes a key between two entities, the initiator and the responder. It can be like TLS 1.3. It can be authenticated with traditional signature keys, but it also supports authentication based on static Diffie-Hellman keys, which means that that the key that is used for is not used for signing the protocol execution, but rather to construct a MAC with a message authentication code with the corresponding entity on the other side of the line. So one particular aspect that is important in the design of the protocol was the transport of certificates. We could see from one of the introductory slides how X509 certificates are quite heavy. And there is ongoing work in the IETF that is standardizing lightweight versions of X509 certificates. But what we did in ad hoc is that we are not transporting the certificate over the wire. We are rather transporting the reference to this certificate that the device can look up locally in a database and fetch. So this means that the heavy certificate, those several kilobytes of data or several hundreds of bytes, depending on the configuration, is not transported over the wire. We support crypto agility. We support different cipher suites based on different elliptic curves, such as NIST P256 or Edwards curves. The protocol is extensible as TLS is. Due to the exchange of ephemeral Diffie-Hellman keys, we support forward secrecy. So we provide forward secrecy, and it is important also to say that in terms of the crypto core of the protocol, we did not reinvent a wheel. So what we did is we took the same cryptographic core that is used by TLS 1.3 and ICE v2, called Sigma I. So this is a cryptographic core published in academic papers and well studied. And we encoded it more efficiently and did some tricks on the actual transport of the messages. So, okay, so that doesn't look right. It's all encrypted. So yeah, so in this slide, I here have a sequence diagram between the initiator and the responder on how the key is exchanged. Typically, what you need to gather from here is that there is an exchange of ephemeral Diffie-Hellman keys here in blue. There is the mutual authentication of the initiator and the responder here in green. And there is the encryption of the identity protection of the roles in the protocol that is performed by symmetric encryption during the protocol. So the core of this, I repeat, is the Sigma I protocol that is standardized, that has been standardized in many different protocols. So as I said, from November 2021 to May 2022, we invited the academic community to study the protocol. And what happened is that there were 4 teams worldwide that responded to this call, meaning that they did some studies in different security models in order to look for vulnerabilities in the protocol. And they did find vulnerabilities. They found vulnerabilities which were later treated and mitigated in the future versions of the protocol before it was being published as an RFC. So what you see here is just a summary of the different attacks that were found by the academic community on the early versions of the protocol in some advanced threat models. So now I would like to talk about the actual performance of ad hoc. So the initial reason why we started the whole standardization process of the protocol. So here on this slide, you can see how ad hoc performs when it is transported over a constrained radio technology called IEEE 802.15.4. This is a constrained radio at 250 kilobits per second, and you can see that has the maximum transmission unit of 127 bytes. So if any message in a protocol is larger than 80 or 90 bytes, depending on the headers of IP headers that get into the packet gets fragmented, and there are multiple transmissions going on the network. So what you can see here is how ad hoc compares to TLS 1.3 in its different configurations. And the most fair comparison would be the ad hoc with raw public keys compared with the DTLS with raw public keys and mutual authentication. We also studied the handshake duration as a metric. How long does it take for the protocol to complete? And the factor of improvement from bytes over the air does not necessarily transport directly into the improvement in the overall duration. So we can see here somewhere around 20 to 30% of improvement of ad hoc with respect to DTLS. And we can also see an interesting graph when a protocol is carried over LoRaWAN, over LoRa radio, depending on the different spreading factors. We can see that DTLS takes almost 120 seconds to complete the handshake, while ad hoc takes, in the worst case, on the order of a handful of seconds to complete over LoRaWAN. And more importantly, ad hoc is compact enough to be transported within the LoRaWAN messages that are limited in size. The last metric that we studied, it considers the memory footprint of the implementation of this protocol. And we can see that our implementation, the implementation that we are leading in Rust programming language at INRIA, is taking around 30 kilobytes of flash memory. A corresponding C implementation would take around 10 to 15 kilobytes, but this is Rust and it's memory safe, so it is, this is where the difference comes from. And in terms of RAM, the implementation of the protocol only uses 2 to 3 kilobytes of RAM for static allocations that are needed by the protocol. So in terms of the ecosystem, ad hoc, there exists more than 7 different implementations of ad hoc. And these implementations are available in different programming languages, such as C, Python, Rust, Java. 3 of them are led by INRIA. Others are led by other interested participants in the standardization world, in the standardization sphere. And all of these implementations have been interop tested for interoperability among each other. As I said, ad hoc is part of the solution. Ad hoc exchanges the symmetric key between 2 entities. There are corresponding works in the IETF which take this key and use the lightweight encryption to encrypt the communication between a constrained device and another internet host. Right now, the IETF Lake working group is working on extensions to this protocol, which include the zero-touch onboarding. So essentially, what I mentioned at the beginning of the presentation, how the Lake protocol can be used for efficient onboarding of devices into the network. It is used with remote attestation, how we can transport remote attestation information on top of the ad hoc protocol. We are working on rekeying, efficient rekeying based on pre-shared keys, and also on status verification of ad hoc authentication credentials in order to make sure that the certificates that are used for authentication are still valid at the time of the execution of the protocol. So now I will just give a glimpse about onboarding with ad hoc. And onboarding is a process of getting a device onto your network. So this is a sensitive process with devices that are lacking user interfaces, because we cannot easily configure them in the field. And we need to come up with protocols that are efficient and smart enough to allow us to deploy the device without essentially touching it for each deployment. So ad hoc, as I said, defines something that we call external authorization data. These are protocol fields which are used for carrying third-party application data on top. And in this case, we are carrying authorization data from a trusted third party that represents the manufacturer that authorizes the device to join the network. So I won't spend too much time on this. What I want you to gather from this slide is that ad hoc is not the only standard in the IETF that is currently being worked on. There exist other standards for that are completing the picture of a lightweight security for Internet of Things. And ad hoc is one of these pieces, important, but one of those pieces that is over there. So I would, if you would allow me, I would just like to wrap up briefly. As we saw, we are working with constrained IoT devices, and constrained IoT devices need security, and it's paramount to have them secure. We are talking about devices with tens of megahertz of processing power, tens of kilobytes of RAM memory, and hundreds of kilobytes of flash memory. So how do they authenticate to the non-constrained internet hosts, for example, and how do they start exchanging protected data? So as we could see, existing internet security technologies can be considered quite heavy for IoT use cases. And we are working in the IETF on a lightweight security stack, including key exchange, but also other pieces to the puzzle that are there to secure the communication of our IoT devices. So that would be all. Thank you.
Malisha Vucinic, merci beaucoup pour cette masterclass.